thank you so much for introducing me, right, and giving me an opportunity to deliver a talk here and try to enlighten my lovable audience, right? So because it's all online, so I do not know whether I will be able to, it's whether I will be able to, uh, uh, satisfy their requirements, because sometimes whenever we take any lectures, right, so we usually, when we go to face, so you will be able to see that in their face expression, so that we can understand whether they understand completely or not. Sometimes this is missing here in online mode, right? So if at all any doubts, anything, if you find during my lecture, so you can always interrupt me and then you can ask me. So that's a good way that I will be able to know also, right, whether you are following every slide of mine, right? Right. So today, so here we'll talk about wireless body area network. So basically I will give certain emphasis on the challenges they are associated with wireless body area networks, as well as some existing solutions, but I will try to make my lecture completely very brief, because we cannot give all existing solution. So but I will overall I'll try to touch every aspects, right? What are different existing challenges in this particular field, right? Okay. So basically, in this lecture I
Thank you, sir.
try to cover up these are the various contents, right? So like we'll talk about wireless body area network in brief, and then we'll talk about a little bit about the MAC protocol that exists in that was provided by IEEE 802.15.6. That's a standard for wireless body area networks, right? So, and then we'll talk about a little bit about interference, and then we will talk about something we have recently published some papers in this particular area. So I will also try to cover those things, right? So that's one of thing is fault and anomalous data detection in wireless body area networks, and also we will be going into a little bit into channel allocation issues, right? And then so we have recently published one paper in IEEE ICC. That's a very popular conference that you know probably in this domain. So we have also recently one of our paper got accepted, that's related to random binary sequence generation. Basically we are trying to create a random binary sequence, right, which will be which will be used as a key in communications, right? Basically whenever you try to communicate, whenever you try to send data from one WBAN sensor to the remote machine, so basically we make use of encryption, decryptions and all. So we make use of certain keys, right? So here we try to generate some sort of key from the heartbeat. So we'll be going to talk about that also, right? And then finally the references. Okay. So here you can see, as per the health monitoring architecture today we have, you can see, so there are certain physiological sensors available in the market, that is a ECG, that is what we call as electrocardiogram, and there is a blood pressure sensor, there is a electromyogram, right, EMG, so which is usually used to measure the strength of muscles, right? And you have a oxygen saturation sensors, and you have a, I mean, ECG, that is what we say, you can always monitor the electrical pulses of your heart, right? So there are various sensors, wireless sensors available, right? So now we need to, so I mean, we need to deploy these physiological sensors on different patients, or you can for regular monitoring also you can deploy these sensors, right? You can attach all these sensors, and then these sensors will keep on monitoring the physiological vitals of the body, right? And then it has to be these physiological vital signs, whatever being captured, right? So those things will have to be sent wirelessly to a remote server, right? Or maybe you can have any sort of database server where you can store those data, right? And those database server can be again further can be given unto a doctor, right? So if you want to make it something remote monitoring, so in that case it will be very much useful, right? So now, so as current standard says that, so I mean each and every WBAN consists of different physiological sensors and a coordinator or a hub. Okay, so basically these physiological sensors, they will send data to the coordinator or the hub, and in turn this hub will transmit the data uh, over internet to the remote server, right? So because of I mean because of this innovative idea, and it is today cost effective also, because the sensors are becoming cheaper, right? And these solutions are also, sometimes you can say they are very user friendly, like you can easily attach these sensors onto the clothes, right? That the clothes that you wear, right? So and then these sensors basically can send data through the hub. Okay, so that means basically you have various physiological sensors and a coordinator or a hub. Okay, so that hub will act as a relay node, right, for a particular WBAN. Now there can be multiple number of such wireless body area networks, right? And different patients, maybe if you talk about any hospital environment where you can think of, like there will be various patients, so these patients can be deployed with these sensors, right? And they are allowed to move within the hospital environment, right? So now right, so then there are different other issues, right? We will talk about that interference issue again, right? So because of we allow these WBANs to move wherever they wanted to within any confined space, so then there is a possibility of a interference, right? So now, so there are these are the various important challenges. We'll talk about that. Okay, so now, so basically it started with in the year 2004, where Golmi et al. So it is a some sort of application. I mean WBAN. I mean based on wireless personal area network. So they developed one WBAN, right? And that's what in the year 2004, and it was published in a military conference, right? That's a Milcom, right? Where it is all based on wireless personal area network. That is based on 802.15.4. Okay, so it's 802.15.4 IEEE standard, right? That's a wireless personal area network, right? It's all like you can think of Zigbee sort of things, right? You have Zigbee devices now available in the market, right? So based upon that, so they designed some sort of medical application, right? So that is one of the work, right, in the year 2004. And then so Mikami et al. So they developed a transceiver, I mean which with the 1 meter range, right? So that means they have developed a short range transmitter basically for medical applications, right? And then another low power wearables wireless sensor interface was developed. Like there was a ECG monitoring system was developed by Perk et al. In the year 2006, right? So based upon this, again based upon this personal area networks only, right? Now, so there are basically because there are some issues in the medium access, because these devices are wireless devices, right? So I mean, as of now, there are shortage of available channels as well as bandwidth in the medical band. So if you talk about the number of channels that you have that are available are very limited, right? Bandwidth is also limited, like the spectrum whatever allocated for this purpose is very much limited, right? Now, so then in that case, so maybe people have thought of, right, if you go with some sort of slot based medium access control protocol, because every node has to every node is allowed to access the channel, right? Because wireless is a completely shared medium, right? Everybody is allowed, should be allowed to share the wireless channel, right? So there are make protocols, right? So there are contention based protocols, and there are guaranteed time slot sort of mechanisms, right? Guaranteed time slot mechanism means they are basically the time division, or you can say slot based MAC protocol, right? They are the TDMA based protocols, right? So now here what we are trying to do is, so now you can go with the slot based MAC protocols, right? They are also suitable, but because they really, these protocols, they really do not require any additional overhead, because every node will be transmitting in turns, right? So that's the reason why it's very simple, right? But because you will not be going to see any sort of collisions, right? Because everybody will be transmitting in their turn, right? But if at all, let's say any of these slots where nodes have no data to transmit, in that case, basically those slots will go wasted, right? So that's the reason why. So if the load is very uniform, then in that case you can go with the TDMA sort of protocols, right? TDMA based protocols. But if the load is not uniform, so basically their contention based approach outperforms, right? So they outperforms these TDMA based, right? We'll talk about that, the contention based, because as per IEEE standard 802.15.6, so the MAC protocol provided in that standard was that it's a CSMA CA, right? So it's a contention based, but we will talk about that super frame architecture of that, so how it all works, okay, maybe in the next slides, right? So that's what here. But one problem with the TDMA mechanism is that, so somehow you need to, I mean, all of the devices, so they will be going to they will be taking part in this content, or taking part in these transmissions, right? So they will have to be synchronized with each other, otherwise so it will be quite difficult, because there should be some sort of synchronization, like time synchronization mechanisms are really required there, because otherwise every device's clocks need to be synchronized to each other, then only they will be able to follow a common schedule, right? Now, so here another Lee and Tan. So transaction and information technology in biomedicine, okay, TITB actually, basically. So there it was published, right? So the first TDMA based MAC protocol for wearable systems, right? So they have also considered like pulse oximeter and body temperature sensors, like, and a coordinator, and they applied TDMA based MAC protocol, and they have given the performance, right? And they have studied the performance of the MAC protocol, right? Now, so we see here certain applications. What are different applications that can be possible for this wireless body area network, right? So now here you have a medical application where you can say that's a remote healthcare monitoring. That means you may be sitting at your home and your health can be monitored from a remote place or from a hospital environment. Maybe you can think of something like this. Maybe you think of some Uttarakhand, the places in Uttarakhand. Sometimes I find some locations are very isolated from each other, right? Maybe they are other part of the hills, right? So there sometimes we find difficulty in providing healthcare services. So in those areas, you can think of developing some applications, okay, these sort of applications, and people can gain advantages of this particular technology, right? So that's what exactly. So maybe telemedicine, it can be also used for telemedicine, right? So, and then It can also be used for some non-medical applications like sports, like where you can have various sensors deployed on your body, and you can always try to improve your gait patterns, right? Maybe Professor Vijay Bhaskar may be going to talk about all these things, right? So that's what, right? You will be having, you can have certain postures, you can improve certain postures, right? So for some sort of sports, or you can always keep monitoring, you can monitor, right, the performance of a particular athlete, right? So, and also it is being used, these things can be used in the military, military places, right? You can always, deploy these sensors onto our army cadets, right? So while we can keep monitoring their health conditions while they are deployed in a very hostile environment, right? And maybe you can always use for lifestyle entertainment purposes also. So there are various applications of these wireless body area networks today. Now here, so it has two different communications in wireless body area network, right? Basically, it has in-body communication, and the other one is a on-body communication. That means in-body means, where you can think of like some sensors can be implanted, right? And there is a medical implant communication system. MICS communication was provided by IEEE 802.15.6. And there is an on-body communication where certain sensors are certain wearable sensors are deployed on the human body, right? And so they can be communicating, right? So now, so it all uses ISM band, right, as well as ultra wideband also allocated for this purpose, right, as per the IEEE 802.15.6. Now, another important issue here is how we are going to provide differentiated quality of service to the through these sensors, right? Because we know that there are various types of sensors available, right? There are various let's say, for example, so if you talk about ECG, if you talk about body temperature, right? So ECG temperature definitely going to get much more priority than the body temperature, because the traffic that will be generated from a ECG sensor will be more, and it needs to be transmitted without any delay. But if you talk about the body temperature, maybe the body temperature, it is going, the traffic will be very much little less, right? Because you you really do not need to send any stream of samples, right? So that is what sensed by sensors, right? So then so there are different priority classes are defined in the standard. So there are 8 different types of priority classes or assigned, right? Now they are starting from 0 to 7. That is what, if the value 0 says that it's a low priority, and 7 means it is a high priority, right? So that is the way that we classified them all, right? Now, so how you are going to provide this priority to these medical different devices, right? So now what we try to do is we have the CSMA, that's the contention based make protocol was exactly provided in the IEEE 802.15.6 standard, right? So where it all uses a contention window, right? So now the contention window range is something like this given, right? If it is a emergency or medical implant event report that need to be sent, so in that case the contention window range will be 1 and 4 in between, right? So that means it gives the highest priority, right? So a random number will be chosen from 1 and 4, between 1 and 4, right? So basically, as per the CSMA CA protocol, we'll talk about that again in the next slide probably. But this is the way that we exactly differentiate different services. Okay, so if let's say if it's a background traffic, or if it is a best effort that you need to give, that means everyone need to be treated equally, right? So in that case, you may be going with the priority 1. And if you want to give excellent effort, yeah, that's what a little better than the best effort. So in that case, maybe you will be giving the second priority, right? And if at all it has any video transmissions, right, or voice data need to be sent from a WPAN, so in that case you can go with the 3 and 4 priority type, right? And if it is a medical data or anything related to the network control, right, so maybe you can go with the priority 5. So, or if at all if it is a high priority medical data that it needs to be sent, so in that case maybe you can go with the priority type 6. Okay, and 7 is the emergency case. Okay, if at all any emergency is happening, if you want to report anything, right, so the devices can make use of this contention window to send your data, right? So that's the way that we exactly we differentiate different services, right? So we provide quality of service. So based upon this context window, basically, you will be able to differentiate in terms of latency, right? So how quickly you will be able to get the channel, right? Now, as part of IEEE 802.15.6 standard, that's a wireless body area network. So the superframe structure was given here like this. Okay, so it has a beacon 1, it has a exclusive access phase, and there is a random access phase, and there is a management access phase, and then again exclusive access phase RAP2 again repeated, and then you have a map, and then there is a beacon 2, and then thereafter there is a cap. You can understand, right? So now basically during beacon phase, so it is what going to provide that let's say the coordinator is going to provide you all the boundary ranges of different phases. Okay, so this is how long a particular phase will continue, and all this sort of information will be sent through a beacon, and thereafter as part of your exclusive access phase, basically the highest priority nodes, they will be containing there. Okay, and then as part of random access phase, so basically here it all applies the CSMA-CA. Okay, so that means it is open for all the nodes, right? So as part of exclusive access phase, so you will be giving the highest priority nodes to contain. Okay, and then from the random access phase, so basically it is a contention phase for everybody, right? Every other node, whatever the nodes that are there, right? So the reason is that so you wanted to give highest priority to the highest priority nodes, okay, because they want to send some sort of emergency data, right? So that's the reason why they will be part of exclusive access phase, right? And management access phase, so that is for basically for polling sort of things. Whenever any coordinator wanted to pull some, some data from polling to get the data from certain sensors, so in that case it will be used. Okay, and there are access with 2 and then you have RFP2 and then MAP and then contention access phase, right? So basically the contention access phase is very much similar to random access phase, right? The same thing will be here, but if any node doesn't get chance to send transmit during these phases, so that will be given chance here. Okay, so during this contention access phase, so in RAP and CAP, so basically the CSMA-CA will be used, right? Now, if you talk about this CSMA-CA, so here is basically it all this CSMA-CA works like this, right? So every node they try to there is a CCA, what you call as clear channel allocation, right? So for a certain duration of time in every slot, so each and every node are allowed to sense the channel, right? So they listen to the channel, right? And if during the CSA duration, so if at all any node finds that the channel is idle, then only maybe they are allowed to reduce the Beckhoff counter value. So that Beckhoff counter value is basically taken from this contention window range, right? So if you see here, there is something like CW mean and CW max. So that is what the minimum and maximum contention values, right? And now, so that is what the way that we have seen there in the table, right? So we have given different contention ranges, right? So now a particular sensor, right, can select randomly a number out from this range, right? And let's say if a node selects a random value between 1 and 4, so what will happen? So that value will be the Beckhoff counter value currently, okay? And now what will happen? So that particular node will every different time slots, I mean, it will continuously, so let's say whole channel is slotted here, right? So now so in every slot, right, during a CCA duration, right, that is what we call as clear channel allocation, right? So during that, the sensor will sense if the channel is idle. In that case, what it will do, it will reduce its Beckhoff counter by 1. Okay, so it will go on for certain time slots, right? And after that, if the value becomes 0, if that counter value becomes 0, then it is allowed to transmit the data, right? So that's what exactly being done, right? So that is what we are explaining here. Now, here is also the CSMA works like that, the same way, right? Only the difference from the CSMA that is there part of 802.11 or any like wireless local area networks, whatever the CSMA-CA is there, it is almost the same thing. Only little difference here is that, so here it allows the maximum retransmissions, that is what the four the maximum retry counter, or you can say retransmissions, are allowed. But in case of 802.11, that's a wireless local area network, there it allows up to 10 retransmissions, right? Maximum 10 retransmissions, right? So it can try for 10 times maximum, right? So if at all, let's say you can think of something like this: if two stations, their value becomes 0, right, at the same time, what will happen? They both are allowed to transmit. If they both transmit at the same time, definitely there will be a collision at the coordinator, right? So that's right. Whenever there is a collision, so they will have to go back, and then again they have to come up with a fresh counter, right? So maybe another random value will be chosen, right? So now here what it does is, if the retry counter, if it is a, I mean, let's say first time we tried with a Beckhoff counter value, right? So let's say we failed. Now again we'll be going into the you will be again trying, okay? So that means you will be trying in the second time, okay? Maybe you will be trying the third time, fourth time, right? So like that, okay? So in the fifth attempt maybe, or because here it is the maximum value is 5, so in this case what will happen? So basically at the fourth attempt, let's say for example, or the third attempt, if it is successful, that is fine. If it is not successful, then it has to go with different contention window, right? So now here it is also going to I mean, it is going to increase this contention window size exponentially, right? It's a 2 to the power of w. W is the value, right? So basically, if the first time the w value is, let's say 1, second time the w value, second time what will happen? If the w value is 2, so in that case it will be 1 comma 2 to the power of 2 minus 1. Then what will happen? 1 comma 3. In the third time, what will happen? Third time w value is 3. That means 1 comma 7. Fourth time, like that. Okay, so basically it is going to pick like this. Okay, so now you have the contention window here, right? And you will be doing that, right? Only difference here is that, so whenever when you are going to keep that contention window stable, and when you are going to keep that contention window increased, I mean, if it is the if this retry counter is same, okay, if the retry counter is if let's say if the retry counter is even, in that case you will be increasing the W value, okay, contention window minimum value. Otherwise, you will not be increasing. That is what exactly we will be doing as part of uh, uh, this CSMSA. That is what you can see here. So basically, we started with the first initialized. We say that retry counter. That means that retransmission is first initially it is 0. Okay, and the contention window is CW minimum max. Okay, and then we try to pick a random value. Okay, and then we try to perform this clear channel assessment. If the channel is idle, in that case, what you will do? So you will be reducing the contention window. I mean, whatever the counter that you have, you will be reducing by 1. Okay, if at some point of time, if the CW value becomes 0, so in that case, it is a success. Okay, that means you are allowed to transmit it. Okay, if no, then you will be doing again the CCA again, right? So if any point of time, if you find the channel is idle, in that case, maybe you will be going and saying that, okay, so it is a retry, no, that's a retransmission. I mean, it's not success. So that means you will be going and retry again. Okay. So and if the retransmission time is, let's say, I mean, this is the first time or second time or third time. So like this, if it is a even or odd, you are checking. If it is even, then you will be incrementing by 1 this contention window minimum value. Okay. If it is odd, that means you will not be incrementing that contention window minimum value, right? So that's only the difference. So even on odd case has been applied here. Okay. Otherwise, everything seems almost the same. Uh, uh, the CSMA protocol that is part of 802.11. Right. So that is the way that we check. Let's say, for example, if this retry counter, if it is greater than or it is equal, if it is greater than this retry maximum counter, in that case, so now finally the node is not allowed to transmit. It will drop that particular packet. Okay. So that's what. Otherwise, it will go and continue. Right. So now. So that is the way the CSMA CA protocol works. So any doubts so far, students? If you have, you can ask me at any point of time. And the packet format that is given as part of this 802.11 802.15.6, that's a wireless body area network. So you have a physical layer convergence protocol preamble. So, and then you have a PLCP header, physical layer header, and then you have a data unit. Okay. So now, so basically, so you have a 90 bits of preamble. So this is usually used to synchronize with the devices, right? Receiver. So for that purpose, you will be actually it's a some sort of a pattern, like it's a alternate zeros and one sort of a pattern will be sent. That's a 90 bits to synchronize with the receiver, right? And you have a physical layer header, right? So where you can see again it's consists of 31 bits, right? So the first 15 bits will goes to the physical header, right? And then you have a header checksum, that is in order to see whether any errors that present in the header itself. For that header checksum being used, that's a 4 bits are required, and there is a BCH parity bits, right? So there are the 12 parity bits. They will be again basically used to increase the reliability of those packets, right? So now as part of physical layer, now you can see, so there are 3 bits physical header. So there is a rate, there is a reserved length. So that rate is, that means here it is reserved, it has 3 bits for the rate. That means it can support up to 8 different rates. But as of now, for the ISM band, so as per the W band, so it supports 4 different data rates, right? So that's so we will go into and we will show you some results there. So and also it's the length takes the 8 bits. It is going to tell you that how much payload that is the part of physical data unit. Okay, that means as part of the data packet, right? How much data it is going to carry. So that is going to tell you the length. Okay, and whether it's a burst mode or not, that means it is through 1 bit you will be telling that the next packet is belonging to the previous packet, I mean to a particular burst, right? So or sometimes there are scrambler seeds being usually used to scramble the data items, input data, right? Whatever the data you are going to send, right? So for that purpose we will be basically using these scramblers, right? Now so you have a MAC header is part of because your PSDU will carry the complete the frame that is coming from the sensors, right? So that again it has a MAC header, like maybe the sender's MAC address, the receiver's MAC address, and the sensor node belonging to a particular band and body area network. So each and every body area network will get a ID, right? Unique ID, and then rest of them are the frame control. 4 bits are the basically used for frame control purpose. Okay, whether it is going to tell that whether this is the particular frame coming from the this coordinator, okay, or maybe this is the frame coming from this coordinator and it needs to be sent to a particular receiver in that particular band, okay, with a band ID of something, right? So these sort of things, so in order to do those sort of things, so you can make use of the frame control again, right? So and then you have a basically the make frame body, so that all allows 0 to 255 octets, and then you have a frame checksum. So basically that is usually used for checking that whether anything errors that there in the frame while transmission, to in order to ensure that, so you going through maybe FCS. Right. So we have basically we have studied with using our NS3 network simulators, right? We have seen that we have created a WBAN framework there, right? And these are the 4 different data rates that supports as per this WBAN, right? So so that's what you can see that starting from 971 kbps and then 481 kbps and then 240 and 120 kbps. For all of them, what we did is here we have varied the number of nodes, right? So if you see n is equal to 8 there, that means here we have considered only 8 sensors part of a WBAN. Okay, now so we have considered all 8 different priority sensors, right? So maybe so one sensor is low priority, then I mean with priority 0, the other sensor will be priority 1, so on, like priority 7, right? So we have considered all different priorities and there are 8 nodes, right? So now, and you can see there, if you are going through those contents and windows, that is what we have provided there, by which if you see how much delay they all take to send the data packets from a sensor to the coordinator, right? So basically, this is the delay that is all saying. Now, now you can see here. So when the number of nodes, you have eight number of nodes in that case, so you see that the below line, so the delay is almost very much close to 0, right? Now when the n value is 16, that means what we did is we took two nodes for each priority type. That means there are 8 priorities, so there are 16 nodes, right? So in that case, again, you can see the average delay is how it is increasing, right? And then Then we increase the number of nodes like 24, right? Where so I mean, for each priority type, there are three different nodes. There are three nodes, right? So in that case, the delay is further increasing. Now, when you going to n is equal to 48, now the see the how the delay is drastically increasing. So that's what, right? And it is with the 971 kbps. Similarly, we have studied the same thing with 481 kbps also, data rate with that also. And then we have studied with 240 kbps also, right? Similarly, we have studied for the 120 kbps also. Now you can see that how the delays are getting varied, right? So that's the way that we do. Now, similarly, we have also made some sort of case studies where case 1, case 2, case 3, something we said like if it is a case 1, that means maybe we mix 25% of high priority nodes and another 25% of medium priority nodes and another 50% of low priority nodes, right? So like that we have for case 1, so 25%, 25 50%, 25%. Maybe case 2 will represent 50%, 25% and 25%. Case 3 like that. So we have given three different cases, and also we varied the number of nodes in the WBN like 8, 16, 24 and 32, and we have observed the delays also, right? So how if at all let's say for example, if you see n is equal to 8, in that case you see, so the delay in case of case 1, you see that. So for D1 means it is very much it's a highest priority. Maybe you have 25% of nodes are highest priority. Okay, so in that case, you see the delay is very much less as compared to D2 and D3, right? So like that. Okay, so if n is equal to 32, in that case also we have taken those percentages, and also you have seen the different delays, right? So definitely, so more number of high priority nodes, definitely it is going to affect the low priority nodes very hard. Okay, because sometimes you will be going to see some sort of starvation sort of, right? So if there are more number of high priority nodes, so low priority nodes they never going to get a chance to transmit the data sometimes. Okay, so that's what we observe through these data, right? We studied this. That's what exactly I said you, right? So maybe we have considered 25%, 50% and 25% low priority nodes. Like this, we have created three different cases, and also and then we observed this how it all affects. Okay, so the low priority nodes, they suffer more average delay than expected. Now, another important issue here, that is what we call as the signal to interference noise ratio, right? So what is a signal interference, right? Because let's say you can think of so there is a W band, okay, A11, that means where A is the coordinator and A1 is the sensor node, you can think of, right? Now so P of A, that can be the received power from A11. Okay, so that is the received power from A11, right? So basically here we try to make use of Freese propagation loss model, right? So and everything made as a constant, right? K, so the like antenna gain and all, so they will be considered as a constant K, and power Tx is the transmitted power, right? And T is the distance between transmitter and the receiver, that means the coordinator and the sensor node. That's, and neta here is the exponent, right? So loss exponent, right? Maybe so as per Freese propagation model, so what they do is, so for example, if it is a free space, That means if sender and receiver, if they are both deployed on the open air, okay, or if it can also happen that sometimes these sensors may be sender and receiver, they might have deployed in the building environments, right, or indoor environments, right, for different environments, so the neta value can be changed accordingly, right. So now what we are trying to say is, so once you get the received power at A, P of A means that's the power received from sensor A11, okay. Now how you are going to calculate signal to interference ratio? So, or sometimes we call them as a signal to interference noise ratio, okay. So here now what we are doing is, now PA that you have received divides, so that power, whatever the power received at the coordinator, that will be divided by the interfering power. That means P of B11. That means the power that will be coming from B11 sensor. Let's say there are these two coordinates, these two W bands are closely operating, okay, or they may be very near to each other, right? So in that case, what will happen? If the coordinator B1, the sensor B11, it is also sending the data to the coordinator B at the same time, right? Now, so I mean that's the power exactly going and arriving at the coordinator A also, right? And that will be considered as a noise. Okay, so you have other noise, like you have sometimes noise floor, like each and every device has like thermal noise, or maybe you can say some sort of noise figure, right, associated with them, right? And so those things will also be associated, right? So now that noise and this interfering noise, that's the N plus P of B11. So these all noise together, so it form a noise again, right? So that's the way that you will be able to calculate signal to interference ratio, right? Now here, so when you're talking about this interference and all, so there are various studies being conducted, right? So like Sun et al. So they carried they carried one study on this interference, right? So they kept like two concurrent transmissions are allowed, and then they observed that what is the packet reception rate, okay. So if at all uh, I mean if the packet when the SIR uh, is below a critical threshold, in that case we have seen that packet reception rate is less than 90%. It is, so that means the number of packets are losing, okay. So that's what, so 10% of packets there we are going to lose. That is what we are saying, okay, indirectly. So they have studied this. Another work also they studied they studied this interference using the mica modes, mica jet modes, right? And also they compared, and they have seen that there is a decrease of 40% compared to when no interference from adjacent channel. So if it and also they have seen that because of the adjacent channels also, so there is a interference, okay, come. So whenever there is an interference or collision, definitely these nodes, they try to transmit again and again those packets. As a result, it will consume more and more energy, right? So that's what, so this is one of the inherent problem with this uh, WBAN. So is part of the IEEE 802.15.6 standard also. So they have not given any solutions for this coexisting of different WBANs, right? So that's one of the challenges. So you all are allowed to carry some work in this area also, right? So there are some studies maybe carried out by considering uh, a TDMA based MAC protocol were used, okay, and they also they studied interference from other such similar systems, right? I mean uh, they have seen that TDMA based two different WBANs coming close to each other, and then they studied the interference level, right? And similarly, so another work where we have seen that Zhang et al. So they also studied some co-channel interference. That means the same channel interference, right? So as well as there is a adjacent channel interference also, right? So they've studied this, and also another paper where they studied like coexisting of WBAN that is based on IEEE 802.15.4, that's wireless personal area networks, as well as 802.15.6 standards. Okay. So now, and also there is no coordination between these different standards, right? So they make protocols, they do not coordinate with each other, right? As a result, definitely they will be leading to some interference issues, right? There will be definitely collisions. Now, there are some cases we have seen that because of this interference. So in some paper, it was reported that because of interference, there was a death casualty happened with the patient. Okay, so that's the reason why, because of the signal interference. So the amount of insulin need to be given to a sugar patient, right? So was exactly given a wrong dose because of the signal interference, right? So as a result, the person died. Okay, so that's what exactly represented reported in one of the journal, right? So that's the reason why it is very much serious, right? So now there are many works in case of multi-hop networks, ad hoc networks. Okay, so where we see there are graph based, there are SIR based, I mean SIR threshold based, maybe channel allocation are being done, right? And also there are some studies like they studied with wireless local area network as well as ZigBee. So based these two different types of networks, if they come close to each other, uh, what sort of impact they are going to give. So definitely, so if you see, if there is a wireless local area network 802.11 and you have a ZigBee, definitely, so because the wireless local area networks, they are the high power networks, so definitely it will leave some damage to the to ZigBee based networks if at all they are they are operated very close to each other, right? So that's what people have studied, okay, in some papers. So that's also another issue, right? And also, to handle this interference, so in various networks and various solutions people have given, like in wireless sensor networks, so you will be scheduling this interference links in such a way that so the total interference of the network will be reduced. Okay, and another solution given by Zhang et al, where what they did is, so they have gone with two different radios, right? Each and every device will comes with two radios, right? One is radio based on 802.15.4, and the other one is based on 802.11. Maybe you can say it's a wireless local area network, or sometimes we call them as a Wi-Fi. Okay, so now what they do is, if at all the node experiences interference in the low power network interface, so it will switch onto the high power network. So that's the way that people are trying to address the solution, right? And also there are some in case of cellular networks, we have seen that there is a power control strategy goes on, right? So like if let's say, for example, if a node with certain power, if it experiences interference, in that case what it will do, in order to make its packets successfully transmitted, so it will increase its power, right? So then maybe after some time, the other nodes may experience more interference, so then they will also keep increasing their power level. So now what they do is, if the total interference is increasing, in that case the devices adaptively they will be trying to reduce their power level so that their success rate will go high. Okay, so this sort of strategy, so power control strategies are also being applied in order to control this interference, like, and there are some game theoretic solutions also have people proposed, right? So maybe this can be so controlling this interference through different strategies, like in game theory. So it consists of different strategies, right? So I mean, strategy means you will be going with any one of the power level, right? So like each and every node will be going with one strategy, so that ultimately, so everybody will be going to get a benefit, right? So that's what game theory, there is a Nash equilibrium, right? So that is what Nash equilibrium was proposed by John Nash. Probably you might have gone through a movie called Beautiful Minds, right? So there you might have seen, right? So that's a movie based on John Nash, right? So that's all related to game theory, right? So you need, everyone need to go with its own strategy so that it should get its maximum benefit. At the same time, it is not going to harm others, right? You need to choose such sort of strategy. That means you need to choose such sort of power level so that you will be able to uh, you know you will be part of the society welfare, as well as you increasing your utility. So that's the way. So there are people are doing in this regard also many works, right? But sometimes we have seen that this is very much difficult with wireless body area networks, because the nodes are here, I mean, they are very miniaturized nodes, right? They are the small nodes, they have very limited battery, and their capabilities are very much limited. In that case, maybe sometimes this adaptive power control may not work, but still people are trying try to achieve. And we have seen another studies we have done to see this interference and all. So you can see some of the snapshots are here. So you can see, like, we kept here n is equal to 1 means here we have considered only one W band. Okay, so when n is equal to 2 means there are 2 W bands. When you have n is equal to 4, that means there are 4 W bands. They are moving within a confined region, right? So, and when they are coming close to each other, so their SINR values are getting changed accordingly, right? So you can report this. So when n is equal to 15, that you can see there, n is equal to 8, 12 and 15. So their average SINR value is coming down, you can see. Okay, so similarly we have again studied same sort of thing with the different attenuation factor, like n eta is equal to 3. Also we have seen that keeping those W bands apart from each other at a distance like 0.5 meters, 1 meter, 1.5 meter, and also we have seen how their signal to interference ratio is varying, right? You can see that, okay, from this. And also, so we have proposed one interference mitigation technique, where we try to, let's say we have two different TDMA based W bands, so they can exchange their solutions, right? I mean, they can exchange their schedules based upon the signal to interference level. They can exchange their schedules, and then after exchanging their schedules, so they will be coming up with a common schedule, and then with that common schedule, the nodes of those two W bands or three W bands will be allowed to transmit. So that is one of the solutions we have proposed, and where we have seen that when we have a common schedule, with common schedule, that is the WCS, and no common schedule, when you do not apply any schedule, so in that case the packet delivery ratio can be. So with common schedule, we have seen that there is a definitely increase in the packet delivery ratio. And also we have studied with this by varying this W-band speed also, right? Because one W-band may be going with 0.25 meter per second, 0.5 meter per second, 7, because basically we the patients, they do not go higher than 1.75 meter per second, right? So we walk very slowly, right? Even we run also, maybe we'll be going 2 meter or 3 meters per second, right? So that's the way that we also studied. We have seen that, right, whenever the speed is increasing, in that case our common I mean with common schedule doesn't work well, because the packet delivery ratio again decreases further, because they come quickly and they go away from each other very quickly. As a result, the we formed a schedule, and then the moment it is you know uh, it is applying, so the node is going away from each other, right? So this is the way that maybe for a low speed, so you can see our scheme is giving better solutions, right? So that's one of them, right? So another work by one of my MTech students, so he did something like he tried to find how to detect this anomalous data, right? Or that means if a sensor is a faulty, so if it is generating any faulty data, so in that case, how you are going to detect, and how you need to classify it, right, as a abnormal one. So he took he took the Physionet. There is a database where he collected this. He has taken the data from there, right? So he took the SpO2 and then pulse and then ECG. So these are the three data he has taken, right? And then what he did is uh, because of the time constraint, so I'll not be talking very you know briefly about what it is all done, right? So you can see that because of sometimes if at all any faulty data is there, so in that case, so it is going to give you a faulty alarms, right? As a result, so the patient will be given some medication which is not really required, right? So we need to identify those faulty data, and we need to detect them, right? So now whatever the existing schemes that are so far available, right? So like people have used different classifier, right? So maybe they are going to do it normal or abnormal using decision tree classifier, right? So they have shown at present the false positive rate is 7.2%, right? But the accuracy is high, okay, 100% almost there. So only thing is that the false positive rate is 7.2%, right? Now we made an attempt here again to you know find that. Okay, so we have applied here deep back propagation neural network, right? And we try to classify them, and then we make use of ensemble linear regression, right? So by which we're trying to predict the values, right? Here we have used ensemble linear regression with that's what linear regression with bagging, right? We have used. So by using that, so we have try to classify them first. Whatever the record that you have, the data, so that will be classified as a normal, abnormal, right? Once it is done, then maybe uh, if at all even if it is the value is abnormal, in that case it is falling outside the predefined normal range, right? And then whatever the classified as abnormal value, and that will be then that value will be predicted using linear regression, right? So basically they are usually used to find the predict the current value for any dependable attributes of the instance using correlated attributes, right? So we have taken this Physionet data, right, where we have taken these many number of instances, and the values are ranging in between these. So right, and then so here is that. So first you applied this PPNN classifier, and then we classify them as a abnormal, non-normal. If it is abnormal, then we are going to predict the value. Okay, if that value is beyond the threshold, then we try to check for 3 times, right? If all 3 times, if the threshold is beyond that value, so in that case, basically we are going to give a alarm. Okay, so that's what exactly we have done so far, right? So we have taken this heart rate, pulse, and respiratory rate data, right? And then so also absolute blood pressure and SpO2, these are things data we have taken, right? And we have seen that the alarm raised by BPNN and SBM model and the J48, that's a decision tree classifier, right? We have compared all of them, right? And then we see that so the alarm raised by BPNN is good as compared to the other ones. You can see the number of false alarms are being generated by them. And also we have seen this because they have a very high accuracy. All of these, I mean, we have tried with BPNN, with SML linear regression, SBM, J48. So all of them gives the true positive, that is the accuracy 100%. But in case of false positive rate, now you can see here it all gives you 4%. That is, I mean, you can see our scheme is giving better results than the existing one. And this is what exactly published in a conference, that is IEEE IBSSC. So it was conducted by IEEE Bombay section, right? And it was held in IIT Bombay. This conference was held in IIT Bombay. So there it got published, right? And here is that you can see that for all of these mechanisms, right? So we have seen the accuracy for bagging and linear regression. Now it is giving almost 98%, right, as compared to other ones, right? And also you can see the mean absolute rate and RMS. That is what we have reported here. Now, so that's what we are able to reduce this false positive rate by using this mechanism. We are able to reduce that. Okay, so successfully we were able to reduce the false alarms, right? Now another attempt was given by one of my PhD student, right? So here we try to integrate wireless body area network with the VANET also. So that is vehicular ad hoc network. So that means you can think of like people are moving on different cars, right? And these cars are they create some sort of an ad hoc network, right? And these vehicles, they can exchange data, or they run different applications, right? On an ad hoc basis, they will be able to create a network, and then they can send data to each other, right? So that's what vehicular ad hoc network. Now vehicular ad hoc network has many more applications, right? There are road safety applications and there are non-safety applications, right? So safety applications, maybe you can think of something like related to road accidents and all, like maybe some sort of messages will be sent to the vehicles, right, saying that maybe you are going with a high speed, or maybe you are not going on a right lane, or maybe after another 100 meters, maybe you are going to face some sort of bump, so go slow. So these are all related to safety sort of applications, or any accidents happen, so you need to quickly send some sort of messages, right? So to the nearest hospital, right? So there are some vehicular ad hoc network, right? Basically, as part of this VANET nodes, there we see that each and every vehicles or equipped with some sort of onboard unit as well as a application unit, that is the application through which it will be sending some data, right? And there is a roadside unit that is sometimes called as RSUs. So in the roadside infrastructure, there are some RSUs deployed, right? And these vehicles will be getting certain services from these RSUs, okay, roadside units, okay. So it's something like some sort of access points, okay. When in case of Wi-Fi, what you're doing is, so usually you have certain access points and you are getting services through that access points, right? Similarly, RSUs also, okay. So now in VNet, so there is a B2B communication, there is a B2 infrastructure, right? So there are two types of communication supported. Okay, so vehicle to vehicle, you can send data from one vehicle to the other, as well as you can send some vehicle to the infrastructure. That means you will be sending the data over the internet. Okay, you want to send to any other place, right? So there are some safety and non-safety applications available, right? So here, we have seen there is a channel allocation problem. That's the one of the important issue here, right? So I mean, how you are going to allocate the channels. Let's say if somebody is facing an accident somewhere, right? In that case, they wanted to send some emergency data, right? And in that case, how a channel will be allocated to that particular vehicle, right? So there are some schemes like RSU centering channel allocation protocol available, right? And right, so there are scheme like Hussain et al. So they also proposed a channel allocation scheme, right? So where the network is highly dense, okay, that means more number of vehicles are there, and these more vehicles are moving with a, I mean, mobility is also high, okay, and it's a some sort of centralized distributed channel allocation scheme, okay. So there it does two ways, right? It has some sort of uh, centralized as well as distributed, right? So that means in distributed means the vehicles will decide, okay. I mean, certain things it will be doing. I mean, the contention windows will be chosen by the vehicles itself, right? Based upon the kind of message, so they will be choosing their contention windows, right? And then the one which will be getting the channel, so will be allowed to send. So there is a mix of it is a centralized and non-centralized. And in case of centralized case, what will happen? Maybe based upon message type. Okay, so now what will happen? Each and every vehicle will be sending that they want to send this sort of message. Okay, so maybe it is an emergency message, highly emergency message, or you can say it is a low emergency case. So there are message types will be there, right? And now based upon the message type, now the RSU will allocate the channel to the vehicles. That's that sort of schema there. So now because of time constraint, so I try to skip some of the literature, but you can see as per our scheme there, what we try to do here is, now there is a OBU and each and every vehicle, right? Now the interesting part here is that our channel allocation scheme, what it does is, now it takes some pride, it takes some criterias, right? So like it all has different criterias like message type, vehicle speed status, channel occupancy level, right? How long the node wants to occupy the channel, what is the vehicle speed, what is the message type. Not only in this work, we try to make use of two other criteria, that is the vehicle speed, how speed at which you are going, right? And how long you want to occupy the channel. So that okay. So now with these different criterias, right, what we are trying to do is, so we are applying a mechanism called TOPSIS, okay. Now, by using that TOPSIS mechanism, we are going to prioritize these vehicles. Like which one is the node that will be given highest priority. That is what the TOPSIS algorithm. And there is a AHP, analytical hierarchy process. So by using that, we will be going to give weights to these vehicles, right? You have whatever the criteria, right? For all of them, you will be giving some weights, right? So by giving some weights, and then after getting some normalized weights for each and every criteria, and that will be then given to the TOPSIS, and TOPSIS finally is going to tell you that okay, this vehicle should be given the first priority, or that will be given the second priority, like this. So now based upon that, so the channel will be allocated. That is exactly what we try to do here. Okay, so like we assume that, so each and every sensor will have this sort of IEEE 802.15.6 interface through which it will be collecting the data, and it will be analyzing that data, particular data, right? And then also, so by using that scheme, so if at all any alert message need to be sent, okay, that will be sent using 802.11p interface. So that message will be sent, right? So here, this is the way that it all works, right? So you can see that, here again, we have given some logic for this pulse sensor module, and temperature sensor module, and blood pressure sensor module, right? So if that, let's say the reading that, whatever the readings that it has, right? If the new reading and the mean pulse reading, okay, and we try to find some sort of difference, right? And if this difference is greater than or less than, or if the person's age is less than 50 or greater than 50, some sort of logic, so then only you will have to generate a alert message. Okay, because maybe you can think of if the age of a particular person is very much less, okay, I mean is a 30 years, 40 years, sometimes maybe the value that the pulse reading that what we obtained may be different, right? And it may not be important for a low age person, right? But if it is a elder person, in that case, so the parameter is very much important, right? So that sort of logic. So we have given for all of these different sensors, right? And we have tried to create these alert messages, right? And based upon those three criteria, now exactly, we have done the allocation. Basically, what we did, so data will be collected from sensors, and it will be processed in the LPU, local processing unit of the sensor, right? Now, and then the alert message will be sent to the OBU. Okay, so OBU now what it does, it will broadcast a beacon message, right? And sorry, it will be given to the OBU, and whenever this vehicle is within the range of the RSU, now it will receive the beacon messages, and then it will send a association request message. Okay, then it will be allowed to then thereafter what will happen, so it will send a channel allocation request, okay, to the RSU. Now what it will do thereafter, the vehicle will send this vehicle data onto the processing unit of the RSU, where so ranks the vehicles based on the three criteria that has been received from the node. Okay, so maybe individual criteria weights, I mean how much weight need to be given to each and every met criteria, so that will be calculated, and then finally by using TOPSIS mechanism, we are exactly ranking all of them, right? So now this is one of the work exactly got published in IEEE ICC 2021. So last this year ICC, so it got accepted, right? And we have presented this work. So now, so that's what we have taken all these three different criterias, right? And then we have applied AHP, finding the weights for individual criteria, and then we applied TOPSIS to rank those vehicles, okay, based upon those criteria values, and then we'll be allocating the channel, right? So that's what we have taken these all different parameters, and then we observed channel allocation delay. So as part of ASP and TOPSIS, basically we need to have a local preference matrix and then a CPM matrix. Like local preference metric means something like this. Okay, we have these are the criteria, and we have 5 different vehicles, right? So if the value is 3, that means it is going to take it wants to occupy the channel for a longer time. Okay, if the value is 1, COL value is channel occupancy level is 0 or 1, that means it requires less amount of time it wants to occupy the channel, right? That way. So so this is the way that a preference matrix will be given, right? And then you need to get a criteria preference matrix, like which criteria will be preferred more over the which one. So that is the matrix we need to create according to SP and TOPSIS. So we created this sort of matrix, and then we studied and we compared that our scheme, when you're going with the proposed scheme, so channel access delay is getting reduced when we increase the number of vehicles, right? And we have seen the channel access delay on the other axis, as well as we have seen the end-to-end delay. So in that case, so our schemes is able to reduce the delay, right? And also we have seen that packet delivery ratio is better, right? And similarly, the throughput is also better, right, as compared to the standard scheme. Standard scheme means whatever the existing. So and WBAN. Now, so then that's all about WBAN and BANET. Yeah, Professor Vishwanath. Yeah, how long I should continue? Can I continue?
Sir, you can continue 5 to 10 minutes more.
Yeah, I'll try to finish all these slides. Maybe another
Yes,
10, 15 slides are there. So quickly I will be going to okay. And then so another work that we have seen here is we try to generate random binary sequences from the heartbeats. Okay, so they will be usually used as a cryptographic keys in the wireless body area networks, right? So whatever so far we have seen, like recent mechanisms, whatever they have today, so right, because these devices are very small, and they will have a limited capability, like limited memory, limited processing and all. So like whatever the existing cryptographic algorithms we have, if you try to implement all them in these small tiny devices, probably it's a very challenging for us, right? So now because to keep this sort of, we need some sort of a scheme by which we can generate some keys. Okay, so now so far as per the literature, right, till now, as per the state of the art, so whatever we have seen, right, so I mean the schemes are able to uh, uh, generate 128-bit RVS. Okay, but that all takes 30 seconds for computation. Okay, so that requires 30 seconds of time for computation, right? I think it's I mean too much, right? So we try to reduce this computation time. Okay, so that's the reason why we came up with some sort of a mechanism by which we try to reduce further this computation time. I mean, it is coming less than 30 seconds, because now it all takes 30 seconds, right? We'll talk about that, how we are going to do that. So basically here in our scheme, what we are trying to do is we trying to apply cyclic block encoding as well as convolutional encoding on a single heartbeat. Okay, and to obtain 32-bit binary encoded value, right? Now in order to get 128-bit, how many such heartbeats need? So we need four heartbeats. So that means with only 4 heartbeats, you will be able to generate 128-bit RBS. That's what So basically, if you see, each heartbeat takes 1 second, so maybe 4 to 5 seconds. So you will be able to generate 128-bit RBS random. So that's what we tried. So now we're going to this. So here what we are trying to do is we have taken MIT arrhythmia database. So they provide ECG related data, right? So we have taken that database, right? So from there we try to extract the RR intervals. RR intervals means the duration between two heartbeats. Let's say if a particular person, uh, that particular person's heart beats at 70, let's say 70 per second. Okay, so that means 70 times per minute, sorry, not second. So per minute, so it beats 70 times, right? Now the RR interval means that's the duration between two heartbeats. Okay, that's the duration, right? We try to take that duration. Based upon that, we try to generate random binary sequence. That's what. Okay, because so nowadays this is also one of the biometric trait basically we are considering. Okay, so will be used as a key in the encryption algorithms, right? To efficiently encode RR intervals using computationally efficient encoding schemes. Okay, so we take these RL intervals and then we try to encode them, right? And we try to see how randomness of this generated RBS, because the RBS random binary sequence that we generated, okay, how random it is, okay, because the more the randomness that you see in a generated string, that will be better for a key, right? We know that, right? So we scrutinize. We tested how our scheme how our scheme is going to work. In terms of randomness. So, and also we have seen how these bit streams are distinctive from each other. Okay, so the random bit binary string sequences, whatever getting generated, whether they are completely distinctive, how distinctive they are, right? So to that, and then we try to encrypt and decrypt the ECG data using those RBS. That is what we have done so far. So you can understand here RR interval what it is. So if you see any ECG data, so there are a P, R, S, Q. So there are 5 different complex that you can see. So that's that peak one is the R. Okay, so R to R interval, right? So this is the duration we are taking. We are taking this duration. What is the interval? This. Okay, so these RR intervals we are taking it, and then we are trying to generate you know random binary strings. Okay, so now here what we are doing is, so from the ECG data, so we take these 4 different RR intervals. Okay, and then what we are trying to do is, so we apply prefix sum to each of the RR intervals, right? And then we apply cyclic block encoding as well as convolutional encoding, both at the same time we apply. So first we applied cyclic block encoding. We have obtained 16 bits from that first RR interval, and also we have obtained another 16 bits from convolutional encoding, right? Now this will together 32 bits, right? So similarly here also for the second RR interval, we also again obtained 32 bits. So 32 bits all together we have obtained 128 bits, right? So that's what. And then we have applied entropy to see how our scheme is better in terms of information loss and all, right? So when we applied cyclic, so we have seen the average entropy 9.9934, but when we applied convolutional, so the entropy is 9929. It's coming down. But when you see when you combine cyclic and convolutional both together, so now the entropy is at 99447. right? So that's what we have, and this is the work exactly got accepted in International Journal of Sensor Networks, InterScience. It's a SCI journal. So, but yet it is not available online, but it's got published recently. Now, so in order to test the randomness, so exactly we have applied 9 different test suits that was given by National Institute of Standards and Technology, right? NIST. It's a USA. So the standards organization, right? So they have given some test suits, right? We have applied all these different tests, and then we have calculated the p-value, right? So for each of these schemes, now if you can see, and if the value that is so whatever after applying these all statistical tests, the values should be in between 0.001 and 0.1. In between the value should be line. Okay, then only that will qualify the test. Okay, so that's what as per that we have qualified in all 9 test cases, test suits, right? And that's what and you can see even also by going through the Hamming distance, whatever the uh, random binary strings that we have generated, right? And we are going to give you, we are giving here the distribution of these binary streams, right? Now if you see that, you can understand the so the distribution, how it all looks like. So in our case, so the distribution is very good, right? Now also we have seen how much power it consumes to run this, compute this algorithm, right? So we have seen that when you apply this cyclic, so it consumes 9.17 watts, right? Whereas in order to compute this convolutional, it takes 9.11, and when you apply this cyclic and convolutional, so it takes 9.14 watts. So it is almost in between cyclic and convolutional, right? So then, and also in terms of memory usage, also we have seen cyclic doesn't require anything, but whereas in case of convolutional, so it requires uh, 0.2 memory in megabytes, right? And if you are going with cyclic and convolutional, it all takes 0.1. So the memory usage for this algorithm is also reduced, right? And execute in terms of execution time, also our scheme is almost takes in between, right? Uh, so what we are trying to say here is, so we are able to come up with better RBS scheme with expenses at the execution time, maybe a little bit memory you required at the as well as different resources are really, I mean, it takes some resources a little bit more, but ultimately it is able to give you a random binary sequences with less time. Okay, so that's what that is the reason why this scheme has got its all. So these are all the references so far we have used in this. So anything, I mean, any questions so far? Anything you would like to ask? Any query?